Hello, everyone. I'm back. I'm back actually with a new topic. I mentioned in last session, Nash equilibrium. Nash was a very well-known guy. I'll come to him a little bit later. But what's the idea? So all the previous examples could be solved by simple elimination of dominated strategies, or sometimes successive elimination of strictly dominated strategies. But there are situations where no matter what you do, you cannot eliminate anymore. And then the question is how to solve the game. Or you can eliminate, but left with some game that, let's say that where one player has two strategies, the other one has 5 strategies, and you cannot eliminate anymore. What do we do then? So, but there are situations where none of the strategies are dominated or none of the remaining strategies after successive elimination of dominated strategies are dominated and the game still has more than one outcome. The next thing to do is to use the well-known concept of strategic equilibrium, Nash 1950, which is known as Nash equilibrium. Let me just give you an example. Just a simple one. Here's 3x3 game. And let's say that this is 1-3. The next is 0-4. The next is 3-5. Then I have 4-0. Then I have 2-4. Then I have 2-2. And then I have 3-5. And then I have 3-3. And then I have 0-4. Let me write this upper, middle, down. And this is left. I call it again middle and right. This is player 1, this is player 2. Let's see if one has any strategy which dominates another strategy. So let's compare up to M. 4 is more than 1, 2 is more than 0, but 2 is less than 3. So I cannot compare up and U and M. What about U and D? 3 is more than 1, 3 is more than 0, but 0 is less than 3. So I cannot compare U to D. What about M to D? 4 is more than 3, but 2 is less than 3. I cannot compare. So I can't do anything with player 1, but maybe I can do something with player 2. Let's compare left and middle. 3 is smaller than 4, 0 is smaller than 4, but 5 is more than 3. So I cannot compare 3 to L to M. What about L to R? 3 is smaller than 5, 0 is less than 2, but 5 is more than 4. I cannot compare L to R. What about M to R? 4 is smaller than 5, but 4 is bigger than 2. Nothing that I can do. The game cannot be reduced anymore. Now, what is the outcome of this game? That's a question. We'll come back to it. So now let's go and say, what is the definition first of a Nash equilibrium by John Nash? A Nash equilibrium is a collection of strategies, one strategy for every player. So if you want to solve the game, you want to ask what strategy every player is going to choose. So the collection of strategy, the choices of the players should be such that no player has incentive to unilaterally deviate from his strategy, given that all other players stick to their strategies. So let me say this. First of all, remember we are under the environment of no binding agreements. We can agree, we can shake hands, we can do whatever, we can talk, but then everyone decides on his or her strategy by him or herself. So now, given that the strategy of each one of us, I want to check, and I'm assuming that all of you, I'm one of the players, and you are many players. Everyone chooses a strategy. I just want to see if this is an equilibrium. So I look on my strategy, and I look on your strategies. Given your strategies, I ask myself, am I happy with my choice? Can I be better off? Suppose I cannot. And suppose that none of you can be better off given what the strategies of the others. In that case, we are at equilibrium point. So actually, if you want, equilibrium point is something which is called self-enforcing. We cannot write binding agreements, but we can have some agreement. And the agreement would be that it should be, in a sense, stable. What does it mean? Once we make the agreement how to play, none of us has any reason to violate the agreement and unilaterally deviate from that. Because if unilaterally, if you deviate from that agreement, you can only lose, you cannot gain anything. Let me read again. A Nash equilibrium is a collection of strategies, one strategy for every player, such that no player, no, not even one, has any incentive to unilaterally deviate from his or her strategy, given that all the others stick to their strategies. Now, it's a big question if people behave in games, in a conflict, when they select the strategy, sometimes they don't talk to each other. They simply select strategies. For instance, firms that compete, they decide on their strategy independent and sometimes simultaneously of the decisions of the other firms. So there is a big question, how do we get to that equilibrium if we cannot sit down and talk and agree? It's a good question. It's like in economics, how prices emerge so that supply equals demand and the market is clear. There are a lot of literature about it, but we are taking it, I'm not asking the question, how do we derive to the equilibrium, but rather what are the equilibrium points, and sometimes we have more than one equilibrium point. Okay, so this is the definition. And by the way, even though he wrote this article in 49, it was published in 1950. And that, look, it's just one page, and for that he got the Nobel Prize. He actually split it with another two. One of them was John Harsanyi from Berkeley, and the other one was Reinhard Zelten from Bonn. They got it in 1994, the three of them, for strategic equilibrium. But the main one that started everything was John Nash. John Nash was a very well-known mathematician that game theory, his contributions to game theory had 2-3 very important papers to game theory. This is one of them. Made a big change in the theory, but his contribution to game theory relative to his total contribution was very, very small. He did a lot of things, lot of things. You can, by the way, go to our Center for Game Theory, Stony Brook Center for Game Theory, to our site, and then you can read about him. He was the only one that got both the Nobel Prize in Economics in 1994 and the Hubble Prize. Hubble Prize. It's a Norwegian on the name of Norwegian mathematician. It's also $1 million for the prize. It is very, very prestigious prize. Some will argue that it's more prestigious than the Nobel in economics. Why? Because every year only one gets it, and mathematicians, you have many more than economists. I'm talking about in the in academia. So he got in, I think, 2015, and on the way back from Norway, he went to back to Princeton. He took a taxi with his wife to go back from Newark to Princeton. There was an accident, and both of them were killed in that accident. So this is John Nash. You can read. I mean, there is a very famous movie on him called The Beautiful Mind. And Russell Crowe played John Nash. I really recommend you to look to watch this movie. Okay, so it looks, the one page that you see here on the screen looks almost words. But if you take one word out, everything collapses. It's really a genius way to write and to prove that every game has a Nash equilibrium. Now, I want to tell you, it looks as if, but for instance, so the game, the article, and for that he got the Nobel Prize, was because from that, a lot of papers came out and a lot of research. But the main idea that every game with finite number of players and finite number of strategies has an equilibrium. And let me give you here a counterexample, as if what he says is wrong, as if. So let me take here 2-1, 1-2, 1-2, 2-1. This doesn't have a Nash equilibrium. Let me show you why. Let's say that the Nash equilibrium that I play up and you play down, you play left. So this is left, this is up, down, and right. If let's say that we make an agreement that I'll play up and you play left. So if I believe that you play left, I have no reason to deviate to down. But if you believe that I'm going up, you have a reason to go from left to right, because from 1 you get 2. So this cannot be an equilibrium arrangement. So let me suppose now that actually I play up and you play R. Okay, is this an equilibrium? Well, if I know that you are playing R, we make an agreement. I play up, you play R. If you play R, I'm better off actually switching to down, because instead of 1, I'll get 2 if you go up. So it cannot be an equilibrium arrangement that I play up and you play R. Okay, I did it with up, now with down. Maybe this is an arrangement which gives us an equilibrium. No, because if I know that you go left, I'm then, and I go down, I get 1. But if I move to up, I'm getting 2. So I have an incentive to deviate from our agreement. So this cannot be. So maybe down and R is the last option. So I play down, you play R, I get 2, you get 1. But if you know that I'm playing down, you're best off moving from R to right to left, because then you increase your pair from 1 to 2. So none of them equilibrium. So how come that John Nash got a Nobel Prize and he didn't see, I mean, that simple game? Of course it's so. However, he allows for more than just 2 strategies up or down, but also strategies that chooses up or down for player 1 at random. For instance, a strategy that you flip a coin. If it's head, you go up. If it's tail, you go down. Another thing, you choose up with probability 1/3 and down with probability 2/3. And so they've also player 2 can randomize. It's called mixed strategies. If you allow for either what we call pure strategies, up is a pure strategy. You don't randomize, you go up. Down is a pure strategy for player 1. Left is a pure strategy for player 2. And R is a pure strategy of player 2. But playing half is another strategy. I don't know, I'm not going for sure to up. I flip a coin and I'll choose one of them at random. If you allow such strategies, where you pick up a pure strategy at random, then you can prove that every game is a Nash equilibrium, either with pure strategy or mixed strategy. I can tell you that actually, I can tell you what is the equilibrium without getting into it now, because we'll do it later in the course. But so this is the equilibrium without getting into details and explaining why. We'll get to that. The only equilibrium of this game is for player 1 to select up with probability 2/3 and select down with probability 1/3. How do you do this? You take 3 pieces of paper and you put on 2 of them, you put up, and on 1 of them you put down, you mix, and you take 1 piece of paper out. If that piece of paper says up, you go up. If it says down, you go down. Similar for player 2, she chooses left with probability 1/3 and right with probability 2/3. If that is the arrangement, none of the players will have any incentive to deviate. If you change it, let's say for player 1 to half-half, you will see that player 2 will have incentive to deviate. It will not be an equilibrium. I don't want to pursue this. We will get into, on that type of a game very thoroughly in the future. Okay, so that one I don't need anymore, so I take it out. And now I want to say that, so let's go into, to some examples and to see how to compute a Nash equilibrium. I'm telling you, it's very, very, very easy to compute Nash equilibrium, but I'll tell you the technique in a few minutes. So look on this game. Player 1 has 3 pure strategies, A1, A2, A3. Player 2 has 3 pure strategies, B1, B2, B3. Okay, the question, what is an equilibrium? Oh, this looks to me very attractive. How to get the 6-6? If I play A3 and you play B2, then we get 6-6. So let's make an agreement. I'll play A3 and you play B2. We shake hands. Would we shake hands? Would we keep or fulfill the agreement? Well, player 1 has all the reason to fulfill it. Why? If player 2 goes B2, and if he moves from A3 to A2, he reduces pair from 6 to 4. If he goes to A1, he gets only 3. So he's happy. What about 2? 2, if player 1 goes A3, is not that happy. She's not that happy because she gets 6. If she goes like this, how much she will get? 7. So this is not an equilibrium. So are there equilibrium in pure strategies for this game? The answer is yes. So first of all, so the only equilibrium will be 5-5. 6-6 is not good. 5-5 is good. Isn't it amazing? But as I told you, when you have the environment, no binding agreements, the only sensible outcome may be inferior. As you can see here, 5-5 is inferior to 6-6. So this is an equilibrium. Let's check that this is an equilibrium. Given that I play A2, you get 5, and you play B1, you get 5. If you move here, you get 4. If you move to our base 3, you get 4.5. You are happy. Given that I go A2, look what I do. I just check the row, but I check the row A2, but the numbers of the column, B1, B2, B3. So there are 3 numbers, 5, 4, 4.5. 5 is the best. And indeed, if you go B1, I go A2, then you are happy. What about me? If you go B1, I know that it depends on what I do. I can get 2, I can get 5, I get 3. Here I get 5, I don't want to deviate. I'm happy. So 5-5 is a Nash equilibrium. Are there more? Let's see here. Here there are no more, but we'll see examples in a second. Okay. So this is an equilibrium. What can I say? The equilibrium is the pair of strategies. The equilibrium is player 1 plays A2 and player 2 plays B1. And the outcome is 5 for me, 5 for you. So the 5-5 is the equilibrium outcome. The equilibrium strategies, or the equilibrium is player 1 plays A2, player 2 plays B1. And now you can ask, is 6-6 an equilibrium, as I showed before? No, why not? Because to get 6-6, by the way, it's very important. When you look on a payoff and say, what is the equilibrium? The first thing to ask, how I get to that point, to the 6-6. Only if I play A3 and you play B2. This is the way to get to the outcome 6-6. So now that you know that I'm going to play A3 to get 6-6, you are better off deviating to B1. Why? Because instead of 6, you are going to get 7. So this is not an equilibrium. So an equilibrium is 5-5. Are there more equilibrium? You can check no, but we'll see in a second how to select all equilibrium points with no problem. Okay. So I hope by now you understand better what is a Nash equilibrium. Let's say with 2 players. It's a strategy for me, I'm player 1, and a strategy for you, you're player 2, such that you do best given what I do. You best reply to me, and I best reply to you. So, given the strategy that I select, your selection is the best. Given the strategy that you select, my selection is the best. And by the way to think of it is if we sit down and agree and I know what you do. But it may be the case that we don't even talk to each other, but then we can ask, tell me what are the equilibrium points. So when I compute the equilibrium points, it's always very convenient to think as if the players sit together, as if, even if they are not allowed to, as if they sit together, they agree on the pair of strategies for each one of them. And now you have to check if both of them happy given what the other one is doing. So the property of a Nash equilibrium that my strategy should be the best reply to your strategy, and your strategy must be best reply to what I do. That's a Nash equilibrium. Okay, so we say this, the only Nash equilibrium is the pair A2, B1, A2 and B1, okay? And the outcome, the Nash equilibrium outcome, the outcome is 5-5. The equilibrium is pair of strategies, A2, B1. The numbers, 5 for me, 5 for you, is the Nash equilibrium outcome. And very, very shortly, we're not going to say every time Nash, Nash, Nash. We'll say equilibrium. Know that 5-5 is inferior to the outcome 6-6. You see, I have 5-5, I have 6-6. Obviously, 5-5 is inferior, which is obtained when 1 chooses A3 and 2 chooses B2. A3, B2, you get the 6-6. But given the choice A3 of 1, player 2 is best off deviating from B2 to B1 to obtain 7. So if I wanted the 6-6, as we said, I have to play A3, you B2, but given my A3, you're better off deviating to B1. 6-6 is not an equilibrium. By the way, 2 things. First, it's enough that one of us has an incentive to deviate that the equilibrium collapses. Number 2, so each one of us, and it's enough that, as I say, that one has incentive to deviate. It's not an equilibrium. Number 2, in order to kill an equilibrium, you have to show me that one of the players have a better strategy, strictly better. Let's say that you got 5, I get 5. But if I deviate to another strategy, I'll get 5. That's not a contradiction. Because why should you deviate if you get the same thing? So you only deviate if you can improve upon, if you can get more, strictly more. So if I get 5 and there is a strategy, other strategy for me that will give me 5, that's fine. It still may be an equilibrium, because in order to deviate, to have incentive to deviate, I have to find a strategy that gives me more. Good. Fine. Now examples. Consider the following 2-by-2 person game. So you have 2 players. Player 1 has 2 strategies to go up or down. Remember all the time, player 1 is the row player. He chooses a row. Player 2 is the column player. She chooses a column, left or right. Okay? And I can see, it's easy to check that up and left is an equilibrium. Why? If we go up left, you get 2, I get 2. If you go left and I deviate to down instead of 2, I'm going to get 0. Not good. So I have no incentive to deviate. Given that I play up, you don't want to deviate to R because you get now 2. If you deviate to R, you get 0. So 2-2 is an equilibrium. But also 1-1 is an equilibrium. As funny as it is. Why? To get 1-1, I have to play down and you have to play R. Once I play down, should you deviate from 1 to 0? No. I mean, to deviate from 1 to 0, meaning to deviate from R to L. No. Given that you play R and I deviate from down to up, I get less. From 1, I go to 0. So this and this are 2 equilibrium points. So actually, this, you can say, but this is better. Okay, let me say about that a few words. I don't say what is better. I just ask what agreements, if we agree upon, would in general be sustained. Namely, none of us has any incentive to walk away or to deviate from that agreement. So I'm not saying you can tell me that 2-2 is better than 1-1. I agree that for the 2 players, 2-2 is better than 1-1. But let's say if you don't know how I choose, I may be drunk and you are not sure. And there is another equilibrium, by the way, with big strategies. When you randomize, and if you believe that I'm drunk, you maybe you want to use that random strategy, mixed strategy. I don't know. These are 2 equilibrium points, and it's not for the game theorists to rank them. Both of them are self-enforcing. Sometimes we rank by this one is sensible, the other one is not sensible. This is the one is very sensible. In what sense? If we agree to, I don't say that we should agree to go, me to go down and you to go up. But if we agree to do this, then none of us has any incentive to deviate. Think of it. We make an agreement, we shake hands that I go down, you go up. Okay, so if I believe that you go up, why should I deviate to up? I may only lose, and the same for you. So, but we'll get to some equilibrium that are obtained with weakly dominated strategies where it doesn't make sense. We'll talk about that in a second. Okay, so let's see how we proceed here. So 2-2 is an equilibrium, but also 1-1. By the way, I said something not very precise. 2-2 is equilibrium outcome. 1-1 is an equilibrium outcome. The equilibrium is up left, up for 1, left for 2, with the outcome 2-2. Another equilibrium, down for me, R for you, with an outcome 1-1. So here are 2 Nash equilibrium points, up left, with the outcome 2-2, and down right with the outcome 1-1. So another example that I want to show you, by the way, it's a famous example, an old example, and it's called the stag hunt. So here's the story. And I tell you who told the story first, but let me first tell you the story. Each of 2 hunters can either try to hunt a stag. A stag is an adult deer that has large meal. I mean, that one can produce a large meal out of it. or hunt a rabbit. What is a rabbit? I mean, tasty, but substantially less filling. Okay? Think of it, I mean, according to our example, think of it as if the stag has 8 pounds of meat, very tasty meat. Very tasty meat. And the rabbit has only tasty, but only 4 pounds of meat. Okay? Now, if an individual hunts a stag, he must have the cooperation of his partner in order to succeed. Let's say we know where the stag goes, the path that it goes, and maybe one should be follow the stag from his back and the other one in front, and in order to catch and kill the stag. So you need the cooperation of the two in order to succeed to hunt the stag. Okay, only one can do nothing. However, a hunter can hunt the rabbit by himself. Now, if both go after a stag, they split it equally and they enjoy the same amount. Let's say if we're talking about 8 pounds, each gets 4 pounds of the stag meat. If only one defects and hunts a rabbit by himself, leaving, by the way, his partner, going after the stag and getting nothing because without him he cannot do anything, that guy that goes after the rabbit gets most of it. So actually he gets the rabbit and leave some small portion to his partner just as a compensation for the bad behavior. If both go after the rabbit, they split it equally. So each of them get 2 pounds of meat. Each player must choose an action without knowing the choice of the other. So that's the story. Story about two hunters that can either hunt a stag or a rabbit. So now I transform this story into the following game. So here is the table. Hunter one has two strategies, two pure strategies, to go after a stag or to go after a rabbit. Hunter two has two pure strategies, the same, go after the stag or the rabbit. Now, if both of them go after the stag, each one gets 4, if you like, 4 pounds of meat, or 4 units of utils. Satisfaction. If both of them go for a rabbit, they hunt the rabbit. There is one stag, one rabbit, 4 pounds of meat, and they split it equally, 2 and 2. If one, let's say player one go after the stag, hoping that the other one is going after the stag, but the other one defects and goes after the rabbit, he for sure will hunt the rabbit. He will have the entire 4, but will leave 1 for his partner not to starve, and he will get 3. And opposite, if hunter 1 goes after the rabbit and hunter 2 goes after the stag, hunter 1 gets 3 and hunter 2 gets only 1. So this is the game. And you can easily check that there are 2 Nash equilibrium here. Let's do it the way, so let's look on it. This is 1. We both go after the stag. Another one, we both go after the rabbit. Why? This for sure, nobody won't like to deviate because 4-4 is the maximum. But why this one is a Nash equilibrium, rabbit. So to get the 2-2, both of us should go to the rabbit. If I deviate, let's say you go after a rabbit and I deviate to the stag, I get nothing. Actually, I cannot do anything. And I'll get 1 because you will hunt the rabbit and you'll be nice enough to give me just 1, not to starve. And you will take 3. So if I deviate here, I'm getting only 1 instead of 2. So I don't want to deviate. Similar if you deviate here, you get only 1. So this is an equilibrium. What about the others? Let me see. Let's say I go for a stag and you go for a rabbit. Is an equilibrium? If you are going after the rabbit, I'm going to get 1. If I go after the rabbit, instead of 1, I'm going to get 2. So I'm better off deviating. So the 1-3 and the similar 3-1 are not equilibrium, and we have just two equilibrium with pure strategies, and both go after the stag or both go after the rabbit. Very good. Now, the stag hunt story was a story that became a game told by the philosopher Jean-Jacques Rousseau that lives in the 18th century from 1712 to 1778. So already there, they were bothered about the two possible equilibrium, and we'll see, what's the difference between them. Another philosopher, David Hume, a Scottish guy, that lived about the same time, provides a series of examples that are stag hunts in a sense. One example addresses two individuals who must row a boat. If both choose to row, they can successfully move the boat and, let's say, cross the river. However, if one doesn't, the other wastes his effort because by himself he cannot do it. Hume's second example involves two neighbors wishing to drain a meadow. If they both work to drain the meadow, they will be successful. But if either fails to do his part, the meadow will not be drained. Okay, there are more examples of this in biology and others. So this is a famous, and a lot of papers were written about the stag, variation of the stag hunt. Some of them with differences of information and all kinds of things like this. But so as I said before, the game has two Nash equilibrium points. Either both go after the stag. This is payoff dominant. Let's look. Why it's a payoff dominant? Because you get the maximum. It's a Pareto efficient. I get 4, you get 4. We can't do it. This is the best outcome we can have in the game. The other one is they both go after the rabbit. And this is risk dominant. Okay? Let me show you about that. You see, if I going after the rabbit is I avoid some risk. If I go after a stag, I may get 4 if you cooperate with me. But if you defect, I take the risk to go from 4 to 1. However, if I go for rabbit, I'm getting for sure either 3 or 2, so I'm getting a minimum of 2. So going after the rabbit, it gives me some assurance of getting enough meat, and therefore it's less risky than go after the stag. So actually, the question is, in this circumstance, should we prefer payoff dominant or should we prefer this risk dominant? So that depends on the specific hunters that play this game. So there are two types of equilibrium. One goes after the payoff to maximize the payoff, taking the risk that if somebody defects, then you end up with 1 instead of 4. The other one is less appealing. You get just 2, but you guaranteed to get at least 2. So these are the two equilibrium, and this is actually, the next the example that I want to show you, the famous example about stag hunt game. Example. The chicken game. What is it? What's the game? So player 1 can either to be tough or to be chicken. Player 2 can also be tough or chicken. So now let's see what's going on in which one of the, in this game. What is the game? So if I'm tough and you're chicken, I'm getting 6, if you like, 6 units of satisfaction from the fact that I really took advantage over you and I was successful. If I am chicken and you are tough, then you get the 6 units of utility, of satisfaction, and I'm pissed off. So I'm getting only 0. Okay. What happens if I'm chicken and you're chicken? Then let's say we cross, there is an intersection, and we behave very careful. I yield to you, you yield to me, and we cross each other in a safe way. In that case, I'm getting 3, you get 3, not as much as you pass by, you don't need to wait, you're playing tough, and you did it fast, but we get some 3 and 3. The problem is when we both tough, we may end up with, wounding each other. In that case, there's an accident and I get -10 and you get -10. That is the game. Look on it for a second and tell me if the game has an equilibrium. And indeed, you have 2 equilibrium points. First, 2 equilibrium outcomes, this and this. One equilibrium is that I am chicken and you are tough. The other equilibrium is the opposite. Let's check, first of all, this is an equilibrium. I am chicken and you are tough. If you are tough, and instead of chicken, I deviate to be tough, instead of 0, I'm getting -10. If I deviate here, I'm getting -10. I don't want it. What about you? Suppose that I'm chicken. If you are tough, you get 6. You go cross, you don't need to wait, you're very happy. If you're chicken, you get only 3. You have to be careful, you move slowly and stuff like this. So this is also an equilibrium. So this, I want to say player 2 also doesn't want to deviate. So actually 0-6 is an equilibrium. Very similar is 6-0. To get 6-0, I have to be tough and you have to be chicken. Given that I'm tough, you're better off being chicken, getting 0 and not -10 if you deviate to tough. Because if you deviate to tough, accident. Okay, what about me? I'm tough, you're chicken, I'm getting 6. If I move to be chicken, given that you're chicken, I end up with 3 only. So none of us has any incentive to deviate. And it's called the chicken game. It's well known, okay? The chicken game that we both try to be very brave, but if we are brave until the last minute, then an accident. If one yield, the other one, so if I'm brave and you decide that you don't want an accident, you get scared, then you're a chicken, I'm getting 6, you get 0. If you are the brave guy and I'm the chicken, I'm getting 0, you get 6. But so there are 2 Nash equilibrium points. So I mean, it's called the chicken game, but in biology, it's well known to be the dove-hawk game. Should I play hawk, tough, or should I play dove, very chicken or safe, moderate? Another equilibrium is the entering a junction. Another story to that game. All of them are represented by some table like this, game like this. Equilibria. Let's see what are the equilibria. You have 2 equilibrium points. Tough chicken that you see 6-0, or chicken tough that also give you 0-6. So now you say, but so who is going to be the tough? Who is going to be the chicken? I don't know. I just say that if the player 1 is playing tough and player 2 is playing chicken, none of them has any incentive to deviate. And we call that pair of strategies a Nash equilibrium. A Nash equilibrium is a pair of strategies. One for me, one for you, so that no one has any incentive to deviate from his or her strategy. Now, how to calculate the Nash equilibrium? It's very, very easy, and I want to first I show you with my pencil, and then we'll see it via the slides. So look, what is a candidate for Nash equilibrium? I ask, is A1, when A1 may be a candidate for Nash equilibrium? So if I play A1, and you play B1, you get 5, but if you play B2, you get 10. If you play B3, you get 7. You play B4, you get 10. B5 minus 3. So the only possible strategies for you so that you are not going to regret when I play A1 is actually B2 and B4. So I designate it with a sign here and a sign here. Namely, your best reply strategy against my A1 strategy is to play either B2 or B4. You're indifferent. Both of them give you 10. So if I play A1, you have no incentive to deviate. Good. And what if I play A2 where you have no incentive to deviate? Namely, what is your best reply strategy? I compare the column 9, 3, because this is your payoff. 12, 10, 9. 12 is the best. I designate here 12 on the right side. Suppose I go to A3. 7, 8, 9, 8, 7. 9 is the highest. So if I play A3, your best reply is to play B3. You get 9. You have no incentive to deviate. Suppose I play A4. What is your strategy so that you have no incentive to deviate? You compare 11, 13, 9, 5, 14. 14 is the maximum. So if you play B5, when I play A4, you're best off. You don't want to deviate to B4 because then you go from 14 to 5. No to B3, you get 9. No to 2, B2, because then you get 13. And now to B1 where you get 11. 14 is the best. Finally, A5. If I play A5, you just compare 9, 6, 8, 7, 6, and you designate the 9. Now we should do, that's not good enough because also when player 2 is playing, I want to be best reply. So let me erase this. And what happens, is there an equilibrium where 2 is playing B1? Well, the only candidate for that is that I play A4. Why? Because I compare 10, 4, 8, 14, 16. If I don't play A4, I will have an incentive to deviate. Let's say I play A1 and you play a B1. Given that you play B1, if I play A1, I will have incentive to deviate to A4 to get 14 and not 10. So actually I designate on the left side the best for me. If you play B2, the best for me, 5, 15, 7, 12, 9, 15 is the best. If you play B3, 7, 4, 10, 10, 8, both 10s. If you play B4, 8, 6, 7, 5, 7, 8. If you play B5, I compare 6, 9, 15, 5, 10, the maximum is 15. Now I look for a square or cell, if you like, where I have 2 stars, this and this. I claim this must be an equilibrium, each one of them must be an equilibrium point. Why? Because if to get to, let's say, A10, I have to play A1 and you have to play B4. Okay? But that's exactly, when you play B4, I chose the A1 to be 8, 6, 7, 5, 7, so I have no incentive. 8 is the best for me. And when I choose A1, B4 is best. If you move to B5, you get -3. You move to B3, you get only 7. If you move to B2, you get the same. So you have no incentive to deviate because you don't increase your payoff. And if you deviate to B1, you get 5 instead of 10. So both of them, so an equilibrium is the one, you do exactly this technique that I show you now, and you look for 2 stars. A square with 2 stars has the property that the strategies that determine this outcome are best replied to each other. That's exactly a Nash equilibrium. Let me erase now this, and you are going to hear it again, but now with no everything automatic. So let's look. Okay. So if I go A1, player 2 should compare 5, 10, 7, 10, minus 6, and I designate the maximum. In this case, both of them are maximum, 10, 10. B2 and B4 are the best reply to A1. Repeat, the strategies B2 and B4 are the best reply strategies to A1. What are the best reply strategy to A2? B3, because it gives player 2 12, all the others give her less. What happens if I go A3? I compare 7, 8, 9, 8, 7. 9 is the best reply, I designate the 9. If I play A4, what is the best reply strategy of 2? Is to go B5 to get 14 and not 5, 9, 13, 11. If I go A5, the best reply strategy of player 2 is to go B1 to get 9 and not 6, 8, 7, 6, which are less. Very good. Now I move to player 2. If player 2 decides to go B1, what is my best reply? I compare 10, 4, 8, 14, 6, and I go for 14. If I move to B2, then the best reply strategy is for player 1. Player 1 compares 5, 15, 7, 12, 9, and goes for 15. So I designate 15. Next, if player 2, go B3, the best reply of player 1 is to go for the 10, 10, namely A3 and A4. Both of them are best reply. I designate both of them. I go to B4, it should be 8 is the maximum, I designate 8. When I go to B5, then the best is the 15 for player 1, and I designate this. Now I look for the square with 2 stars, and we can see there are exactly 2 Nash equilibrium points. A1, B4, that gives us the outcome 8, 10, and A3, B3 with the outcome 10, 9. So the question, what if I have 2, what should I play? That is not, there's no clear recommendation. I just tell you what are the 2 possibilities that one is best reply to the other, namely that if we make an agreement, none of us has any incentive to deviate from that agreement. Self-enforcing agreements are 1, A1, B4, in which case, when they do it, then player 1 get 8, player 2 get 10, and the other one, A3, B3, and when they take these decisions, player 1 get 10 and player 2 get 9. I don't compare the 2, I just say in case they agree on A3, B3, none of them has any incentive not to fulfill the agreement. They, each one of them will stick to the agreement, believing that the other one does it. Is there any easy way to find all Nash equilibrium points of the game? The answer is yes. Here's the procedure. I just described you the procedure. We put for every strategy of player 1, every row designated by star, the upper right side of the square containing the highest payoff of player 2. If I go A1, I designate the highest payoff of 2. Remember, when I look on the strategies of 1, I designate the highest payoff of the other player, player 2. And when I look on the payoff of the strategy of player 2, let's say B3, I designate just the highest there, which is 10 and 10. And I continue this way until I'm getting 2 stars. That's what's written here. And so now I want to give you one more example. First of all, look here, and then this is a little bit of a problem. You see, in this one, we have 2 Nash equilibrium points. This, which is trivial, but this is a Nash equilibrium. Why? If I play B and you play beta, then I get 0, 0. Look, why it's Nash equilibrium? If I deviate from B to A instead of 0, I'll get 0. And if you deviate from beta to alpha instead of 0, you get 0. So technically, it's a Nash equilibrium. But this B is weakly dominated strategy for player 1. By the way, beta is strictly dominated strategies for player 2. So actually, this equilibrium is obtained when we use weakly dominated strategies. That doesn't make sense. So this Nash equilibrium doesn't make sense. Why? Because it doesn't make sense that a player will use weakly dominated strategy. Because if it is a weakly dominated strategy, there is another strategy which dominates it. So he should deviate to the other strategy. A dominates B. I cannot lose only, why to play BB if I can play A, where I can get at least as much, 1 is more than 0, or the same. So there's no reason in the world that I'll go for B. It's weakly dominated. 0 is less than 1, and the other 0 equal to 0. Also, beta is weakly dominated. So what I demonstrate to you that first, you may get non-sensible equilibrium points only when it's weakly, when one or both players have weakly dominated strategies, and when the in equilibrium, one of the players or both of them use weakly dominated strategy. By the way, and bear it in mind, it's a very important point that I'm going to tell you now. There is no equilibrium where one of the players is playing strictly dominated strategy. Why? Because if there is another strategy that strictly dominates this strategy, meaning that no matter what the other one will do, I'll get more, then I'll deviate because I'll get more. Here I have no incentive to deviate because instead of 0, I don't get more. I get 0. But let's make this one strictly. Suppose that instead of 0, 0, I have here 0.1, 0.1. Now it is strictly dominated. 1 is more than 0, 0.1 is more than 0. This now cannot be an equilibrium because if I play B and you play beta, I'm better off going A because 0 is less than 0.1. The problem is only when you are indifferent between two choices, given what the other one is doing, and you may, as demonstrated here, you may get an equilibrium where one or both of the players are choosing weakly dominated strategies. Okay? It cannot be an equilibrium when one or both of the players choose strictly dominated strategy. Okay. We are almost there. We have one other example that I want to show you. So here, first of all, what's written, the strategy B and beta are dominated. And therefore, if you eliminate this, the only sensible one is 1, 1. However, after eliminating these strategies, we left with the strategy combination of A and alpha, which is an equilibrium of the original game. However, the combination B beta is an equilibrium of the original game that was eliminated. So by elimination of weakly dominated strategies, we may eliminate some equilibrium strategies. But what equilibrium strategies that are not sensible? There's no, it is not sensible for player 1 to use B because A gives him either more or the same. Same for player 2, choosing beta is non-sensible for player 2. Here's another example. Okay, consider the following 3x3 two-person game. This is really a striking example. The example is the following. Look, the best that both players can achieve is 1-1. And obviously it's an equilibrium because you cannot deviate and get more than one. The maximum payoff of each one of the players here is one. So actually this looks very, very attractive. How to get it? I play A1 and you play B1. I think that if I give you and you are not very experienced, you would think that that is the right choice. I play A1 and you play B1. Let's shake our hands, let's agree, and we go home. Should we deviate? Well, I can tell you, and this is the only equilibrium. Let us check that this is the only equilibrium with the same argument that we had before. I'm talking about equilibrium in pure strategies, not with randomizing. That we'll get to the later stage. So as before, if I play A1, 1, 1, or 1, you designate all of them are maximum. If I play A2, 0, 0, 1, you designate the 1. If I play A3, 0, 1, 0, you designate this one. If you play B1, I designate all of them. If you play B2, I designate only this. If you play B3, I designate only this. The only one with 2 is this one. So first of all, this is the unique equilibrium where players play with pure strategies, namely they don't randomize the strategies. Good. So once I observe it, I say, yes, but this is a stupid equilibrium. Nonsensible. Okay, and let me tell you why it is nonsensible. Look, A2 weakly dominates A1. Why? If you go B1, I'm indifferent between A2 and A1. I'm get 1 and 1. But if you play B2, 1 is better than 0. And if you play B3, 0 is like 0. But there's no reason in the world to play A1, no matter what you do. If you decide to go B1 and I go A2, here I get 1, here I get 1. But I'm afraid that if you go B2 and you have good reason maybe to go to B2, then if I go A2, I get 1 more than 0. If you go to B3, I don't care. So actually, I mean, if you compare A1 to A2, for sure A2, it's better than A1. Okay? Moreover, even A3 is better than A1. Why? Because 1 is as 1, 0 as 0, but 1 is more than 0. So I can tell you, if I have to rank the 3 strategies, I don't know how to compare A2 to A3, but I know that A1 is worse than these two. Now, by symmetry, I mean, that's how I designed the game. Also, B2, also player 2, look, B1 is weakly dominated by B2. 1 is like 1, 0 is like 0, but 0 is less than 1. Moreover, B1 is weakly dominated by B3. 1 is like 1, 0 is smaller than 1, and 0 is like 0. So I don't know what to recommend to player 2, but I can tell player 2 one thing: don't play B1. B2 is better or B3 is better. I don't know what to tell you, but don't play B1. And I can tell player 1, if you are rational, don't play A1. If you play A2, you get at least as much as A1 and maybe more. If you play A3, you get at least as much as A1 and maybe more. So actually, this equilibrium, the only equilibrium of the game is nonsensible. The only Nash equilibrium here is A1, B1 with the outcome 1, 1. This outcome is the best outcome in the table, but it is not sensible. Note that A1 is weakly dominated by both A2 and A3, and B1 is weakly dominated by both B2, B3. I want to tell you something. Even if we make an agreement, I play A1, B1, why should I believe you that you'll stick to the agreement? If you move to B2, you get at least as much as maybe better. Why should I believe maybe you go to B3, where you can get at least as much, 1 and 1, 0 is less than 1, 0 is like 0. So I should not believe you that you go B1, and you should not believe me that I go A1. And this actually hurt us. because we cannot believe each other to do this, to fulfill this agreement, because for me to believe you, I should believe you that you take a nonsensible action. You have better actions. Okay? Even though this is an equilibrium. So actually, I would take this out and this out. The relevant game is this. This has no equilibrium in pure strategies, and the only sensible equilibrium actually is to play A2, A3 with probability half-half. We'll get to that. And to play B2, B3 with probability half-half. And what do you get? We get half for me, half for you. Because in these games, sometimes I win, let's say that's win-lose in this game. Sometimes I win, you lose. I lose, you win. I lose, you win. I win, you lose. So on average, once I lose one, so the equilibrium will be that we have to flip a coin and to play it half-half. And what do I get? On average, I'm getting half. So I could get 1-1, one for me, one for you. This is not sensible. And this is an equilibrium. This is not sensible equilibrium. There is another equilibrium, more sensible, where we get less. Isn't it interesting? And so once you have a strategic conflict, all kind of very interesting things can happen. Okay, let me see if we say anything about this. Here what we do. The only Nash equilibrium here is A1, B1 with the outcome 1-1. This outcome, we say this, okay, so we get this, and that's it. I told you the half-half, I didn't put it here. Okay. I think that we'll get to sensible equilibrium. We have to do, you see, you know what, let me finish this one before we go to the traffic equilibrium, which will be completely a different video. So know that in equilibrium, no player uses a strictly dominated strategy. Of course, otherwise, if you use strictly dominated strategy, it means that there is another strategy which gives you more. But if you get more, you deviate. Otherwise, he's better off deviating to the strategy which strictly dominates it, because then he gets more no matter what the other one is doing. So let me now make a definition. A strategy is sensible if it is not weakly or strictly dominated by another strategy. Otherwise, the strategy is non-sensible. An equilibrium is sensible if no player chooses a non-sensible strategy. Okay, by the way, that means that you don't choose weakly dominated strategy. Again, in equilibrium, it's impossible that you choose strictly dominated strategy. Otherwise, if you have strictly dominated strategy and you use it, it's not an equilibrium because you're better off deviating to the one that strictly dominates it. So I should actually say an equilibrium is sensible if no player chooses a non-sensible strategy or weakly dominated strategy. Okay, let's look on the following example. So here is a game. Player 2 has 4 strategy. Player 1 has 4 strategies. And I can see that I can eliminate D. Why? Or maybe I can eliminate first C. Let's eliminate first C. Okay? Actually, it doesn't matter. Let's say that I eliminate first C. Why? C is weakly dominated by A. 2 is less than 4. 4 is less than 5. 4 is like 4. And 3 is like 3. So C is weakly dominated. I can also take D out because D is actually weakly dominated by A, for instance, by A. 3 is less than 4, 0 is less than 6, 4 is like 4, and 3 like 3. So actually I can say that D is weakly dominated by A. Therefore, I can take these 2 and I left with 3 by 3. Okay, can I take more? Okay, just a second. So first of all, uh, eliminated these two strategies. Probably I cannot eliminate more. You check that there is no way. Let me check with you. Compare now A to B. 4 is more than 0. 5 is less than 6. Cannot compare. Compare A to D. 4 is less than 5. 5 is more than 4. No. And it's similar for 2. However, when you look on it, you see that actually, we can find out all the equilibrium points of the game before we do it, but you see that actually, what are the Nash equilibrium points? 3-3 is a Nash equilibrium, was eliminated. Sorry. Yeah, it was eliminated by D. Why it's a Nash equilibrium? Because 3 is like 3, it's more than 2, it's like 3, none of, you know what? Let me first, before we go to eliminate, no, I don't have it. We put it already. But let's say that, let's find first what are all the equilibrium points. So if player 1 goes A, player 2 compare 4, 1, 2, 3, the best reply is 4. 6, 0, 4, 2, the best reply is strategy A to get 6. 2, I forget about elimination. I do for everyone. So if player 1 is going C, she compares 4, 2, 2, 4. We designate this and this. If he goes down, we compare 3, 2, 0, 3. I designate both 3s. Now, if she goes small a, 4, 0, 2, 5, I designate the 5. If she goes B, small b, 5, 6, 4, 4, I designate the 6. If she goes small c, 4, 2, 4, 6, I designate the 6. If she goes D, 3, 2, 3, 3, I designate the 3s. How many Nash equilibrium I have? 1, 2, 3. 2 of them are non-sensible because, for instance, these 2, 3, 4, and 3, 3, you get them if player 2 is playing D, but D is weakly dominated by A, so it's not sensible. So I can say that the only sensible equilibrium is that player 1 plays D and player 2, she plays A. Hence, the only sensible equilibrium is DA. These two equilibrium are equilibrium points by definition, but are not sensible because someone uses, someone I'm talking about, player 2, to get this, must play down D, and D is weakly dominated by A. Why should player 2 play D, where if she plays A, she gets either the same or more? 6 is more than 0 and 4 is more than 3. Okay. We see that a Nash equilibrium may consist of weakly dominated strategies. No strictly dominated strategy can be part of a Nash equilibrium. I say why, but we answered the slide before. Let us also mention that this game has other Nash equilibrium points, but in mixed strategies that are selected by random device which do not use any weakly dominated strategies. Okay, I think that this remark is really in parentheses, sorry. It should come later on, but find out, so you can eliminate for now. Every player uses the strategy, it continue. I don't want to get, we will study mixed strategies later on, so you don't need to take it. Actually, it's irrelevant for this point. Okay. This is good for now, and will be soon again with traffic equilibrium, a very exciting material. Thank you, and we'll see you very, very soon.